Welcome back to AI Academy. Today, we're diving into one of the most elegant and powerful algorithms in machine learning, Naïve Bayes. By the end of this video, you'll understand exactly how this algorithm works, when to use it, and why it's called naive, despite being incredibly effective. Let's get started. In the next 15 minutes, we'll cover 5 key areas. First, we'll understand what naive Bayes actually is and the mathematical foundation behind it. Then, we'll explore the different types of naive Bayes classifiers. We'll look at real-world applications where this algorithm shines. I'll walk you through a practical example so you can see it in action. Finally, we'll discuss the advantages and limitations you need to know about. Before we dive into naive Bayes, we need to understand its foundation, Bayes Theorem. This theorem tells us how to calculate the probability of event A happening given that event B has occurred. The formula might look intimidating, but it's actually quite intuitive. P of A given B equals P of B given A times P of A divided by P of B. Think of it as updating our beliefs based on new evidence. Let's make this concrete with an example. Imagine you want to know the probability of rain given that the sky is cloudy. Bayes' theorem helps us calculate this by considering how often is the sky cloudy when it rains, what's the general probability of rain, and how often is the sky cloudy overall. This is exactly how naive Bayes thinks about classification problems. Naïve Bayes is a probabilistic machine learning algorithm used for classification tasks. It's based on Bayes' theorem and makes a strong assumption that all features are independent of each other. This is where the naive part comes in. In real life, features often depend on each other, but this algorithm assumes they don't. Surprisingly, this naive assumption often works remarkably well in practice. The algorithm is called naive because it assumes feature independence. For example, in email spam detection, it assumes that the presence of the word free is independent of the word money appearing in the same email. We know this isn't true. These words often appear together in spam emails. But this simplification makes the algorithm computationally efficient and surprisingly accurate. Here's how naive Bayes works mathematically. For classification, we want to find the class with the highest probability given our features. Due to the independence assumption, we can multiply the individual probabilities of each feature. We calculate this for each possible class and choose the one with the highest probability. The denominator is the same for all classes, so we can ignore it during comparison. There are 3 main types of naive-based classifiers, each designed for different types of data. Gaussian naive Bayes is used when your features follow a normal distribution. Think of continuous numerical data like height or temperature. Multinomial naive Bayes works with discrete count data, perfect for text classification, where you're counting word occurrences. Bernoulli naive Bayes handles binary features, things that are either present or absent. Gaussian naive Bayes assumes your features follow a normal distribution. It's perfect for continuous numerical data. For example, if you're classifying flowers based on petal length and width, or predicting customer categories based on age and income, the algorithm estimates the mean and standard deviation for each feature in each class, then uses these to calculate probabilities. Multinomial naive Bayes is the go-to choice for text classification. It works with word counts or frequencies. Think about email spam detection. The algorithm counts how many times each word appears in spam versus legitimate emails. It then uses these counts to classify new emails. This type is also great for document classification and sentiment analysis. Bernoulli naive Bayes deals with binary features, things that are either true or false, present or absent. In text classification, instead of counting word frequencies, it only cares whether a word appears or not. This can be more effective when the presence of a feature matters more than how frequently it occurs. Naïve Bayes shines in many real-world applications. It's incredibly popular for spam filtering. Your email provider probably uses it right now. It's excellent for sentiment analysis, determining whether reviews are positive or negative. News categorization, medical diagnosis based on symptoms, and real-time predictions all benefit from Naïve Bayes. The algorithm is fast enough for real-time applications and works well even with limited training data. Let's walk through a practical example. Imagine we're building a spam detector. We have emails labeled as spam or not spam, and we want to classify new emails. Our features might be words like free, money, urgent, and meeting. We'll use the training data to learn the probability of each word appearing in spam versus legitimate emails. In the training phase, we calculate several probabilities. First, the prior probability. What percentage of emails are spam overall? Let's say 40% are spam. Then, for each word, we calculate the likelihood. How often does free appear in spam emails versus legitimate ones? Maybe free appears in 60% of spam emails, but only 5% of legitimate ones. We do this for every word in our vocabulary. Now comes the prediction. We receive a new email containing the words free and money. We calculate the probability this email is spam by multiplying the prior probability of spam by the likelihood of each word appearing in spam emails. We do the same calculation for legitimate emails. The class with the higher probability wins. If spam probability is 0.85 and legitimate is 0.15, we classify it as spam. Naïve Bayes has several compelling advantages. It's incredibly fast. Both training and prediction happen quickly, making it perfect for real-time applications. It works well with small datasets, unlike deep learning models that need massive amounts of data. It's not sensitive to irrelevant features and handles multi-classification naturally. Plus, it provides probability estimates, not just classifications, which can be valuable for decision-making. However, Naïve Bayes has important limitations. The independence assumption rarely holds in real life, though this often doesn't hurt performance as much as you'd expect. It can struggle with feature combinations. If features work together in important ways, the algorithm might miss these relationships. It's also sensitive to skewed data and can be overconfident in its predictions. For continuous features, assuming normal distribution might not always be appropriate. So when should you use Naïve Bayes? It's excellent for text classification tasks like spam detection, sentiment analysis, and document categorization. Choose it when you need fast predictions, have limited training data, or want probability estimates along with classifications. It's also great as a baseline algorithm. Start with Naïve Bayes to establish a performance benchmark, then try more complex algorithms if needed. Here are some tips to get the most out of Naïve Bayes. For text data, try different pre-processing techniques like removing stop words or using n-grams. Laplace smoothing can help handle words that don't appear in training data. Feature selection can improve performance by removing irrelevant features. And remember, sometimes the simple Naïve Bayes algorithm outperforms more complex models, especially with limited data. Let's recap the key points. Naïve Bayes is a probabilistic classifier based on Bayes' theorem with a strong independence assumption. Despite being naive, it works surprisingly well in practice. There are three main types for different data types. It's fast, efficient, and great for text classification. While it has limitations, it's often the perfect tool for the job, especially when you need quick results or working with limited data. Now that you understand Naïve Bayes, I encourage you to try implementing it on a real dataset. Start with a text classification problem, maybe sentiment analysis of movie reviews or product reviews. Most machine learning libraries have built-in Naïve Bayes implementations, so you can focus on understanding the results rather than coding from scratch. That's a wrap on Naïve Bayes. I hope this gave you a solid understanding of this powerful algorithm. If you found this helpful, please hit that like button and subscribe for more machine learning content. In the comments, let me know what algorithm you'd like me to cover next. Thanks for watching, and I'll see you in the next video.